So we were talking about spin one particles. And so let's just recap. We had our operators, our angular momentum operators for spin one were Jx, which is h bar over the square root of 2, and then we had 0, 1, 0, 1, 0, 1, 0, 1, 0. We have jy, which is again h bar over the square root of 2, and this time we have some i's. And then we have jz, which was h bar without the factor of square root of 2, and it's just 1, 0, minus 1, with zeros everywhere else. Okay, so those were the angular momentum operators, and we defined our states, the base states. Are defined as the top state is 1, 0, 0. We have the 0 state that is 0, 1, 0, and then we have a bottom state, minus 1. That was 0, 0, 0, 1. And these states satisfied that Jz operating on the top state would give h bar times the top state. Jz operating on 0 gives 0 times the 0 state, and Jz operating on the bottom state gives minus h bar, minus 4. And j squared, we defined j squared which was jx squared plus jy squared plus jz squared, and j squared we found was 2h bar times squared times the identity matrix. And so that j squared on any of these base states just gives 2h bar squared times the base state. Okay, so this wasn't much different than what we did for spin 1/2. But now we're going to define some new operators that have a lot of utility. And so let's define some new operators that are called the ladder operators. And we'll define j plus, which is j sub x plus I j sub y, and we'll define j minus, which is j sub x minus I j sub y. Okay, and so collectively, I'll call these j plus minus, which is jx plus or minus I j sub y. So what are they? Well, if we calculate j plus, this is equal to jx, so that's h bar over the square root of 2, 0, 1, 0, 1, 0, 1, 0, 1, 0, plus I times jy, which is also h bar over the square root of 2, and it's 0, minus I 0, I 0, I 0, minus I 0. Oops, minus is there. And so what do we have? Well, when this I hits this I, this gives us a minus 1, we'll get a plus 1, we'll get a minus 1, and we'll get a plus 1. So these minus ones here, we'll cancel these here, and then we'll get some additions for these ones there and there. And so this is h bar over the square root of 2, 0, 2, 0, 0, 0, 2, likewise, J minus, if you calculate it, I'll have a minus I, so these ones will, the top right ones will cancel and the lower left ones will add, and so then we'll have H bar over 2, 0, 0, 0, 2, 0, 0, 0, 2, 0. So those are that's the form of the plus and minus operators. Oops, this is a square root too. Okay, so let's take a look at what happens. Let's see, let's write this also. Let's pull out the 2, so this is the square root of 2 H bar 0, 1, 0, 0, 0, 1. And this is root 2 H bar. Okay, so there's just 1s there. And now let's see what happens when we operate on our base states. Okay, so let's look at J plus operating on the state minus 1. So this will be the square root of 2 H bar. And now this matrix has to operate on this column vector. So the top one will give me a 0. The second row there will, when operated, will give me a 1, and then I'll get a 0. So this becomes 0, 1, 0, and it becomes the middle state. So this becomes 0. And then J plus operating on the 0 state. Now you have to think about what this matrix is going to do when it operates on this state. Well, the top row, when it operates, will give me a 1. And then the middle and bottom rows will give me 0. So I'll get 1, 0, 0. So this will take this state to square root 2 H bar 1. And then we can finally ask what happens when J plus operates on the top state. And you can see that that matrix, when it operates on this column vector, will just give you 0, 0, 0. So this gives a 0. Okay, so it brings you up from the bottom to the top. And now we can do the same thing with J minus, and let's start with the top state. Well, that will give you square root 2 H bar. And now we're operating on the top state with this matrix. So we're going to operate on this column vector, so we'll get a 0, 1, 0, which will be the middle state. So this takes us to 0. And then J minus on 0 will just give you minus the bottom state, and then J minus on the bottom state is 0. Okay, and so those are the ladder operators. And these are important for dealing with angular momentum, because remember, these 3 states are angular momentum states. So this is the Jz has the highest value here and the lowest value here. Jz is it's the projection of the angular momentum on the z-axis. And so what we're doing is we're moving up and down the possible values of Jz with our ladder operators. So the ladder operators move up and down the angular momentum base states. Okay. So you can think of it as a ladder. So with three rungs, where we have the top state, the middle state, and the bottom state. And you can go, J plus takes you up the ladder, J minus takes you down the ladder, and then if you get to the top rung and you try to go higher, you get 0, and if you're at the bottom rung and you try to go lower, you get 0. So it takes you off the ladder. Okay, now we established before that JX dagger is equal to JX. So that's obvious for JX because the transpose of this matrix is the same and there's no complex numbers. But for JY, it's correct also, because when you swap these i's over here and then you conjugate, you'll get the same matrix back. And then JZ is again, obviously, Hermitian. So we have these operators here are Hermitian. So now let's go ahead and let's do some calculations, because now that we have some new operators. We just defined J plus and J minus, and we established already also the commutation relations between Jx, Jy, Jz, and J squared. And now that we have our new operators, we want to find out how they interact with Jx and Jy and so on. So first, let's note that if J plus here is Jx plus I Jy, so J plus dagger equals Jx dagger minus I Jy dagger. But Jx and Jy are Hermitian, so this is just Jx minus I Jy. So we have that J plus dagger is equal to J minus, and J minus dagger is equal to J plus. Okay. And now let's calculate the commutation relation between Jz and J plus minus. So this is going to be Jz, J plus minus, minus J plus minus Jz. Okay, so this is Jz times Jx plus minus Ijy minus Jx plus minus Ijy times Jz. And that's just, let's collect the terms. So this is Jz, Jx minus Jx, Jz. And then now I have to calculate the terms with this plus minus. So we'll have plus or minus I. Actually, I'll get a minus sign here. I'll have minus or plus Ijy. Oops, sorry, that's right. Plus or minus Ijz, Jy, minus plus Ijy, Jz. Okay, so this Jx, Jz, Jx minus Jx, Jz, this is just Jy. This is I h bar Jy from the commutation relations that we wrote down before. jx, jy, well, jz, jx is h bar jy. So that first term is that. And then we have, we can pull out plus or minus I, and then we'll have jz, jy minus, let's pull out the plus I, and then we'll have plus minus jz, jy minus plus jy, jz. And so in this expression, you can either take the top signs or the bottom signs. But if we take the top signs, we have jz, jy minus jy, jz. That's out of order. Remember when we have x goes to y, goes to z is the rule for keeping the plus sign here. So that gives us a minus. So we'll have here I h bar jy plus I, and then we'll have minus plus I h bar jx. Okay, so then we have this I will give us a minus 1. And so ultimately then we'll have jx, we'll have I h bar jy plus minus h bar jx. And this is equal to plus or minus h bar jx plus or minus ijy. Okay, so what we just found, this is just j plus minus. So what we just found is that the commutator of jz with j plus minus will give us plus or minus h bar j plus minus. Okay, so this is two commutation relations. You can take the plus sign and you can take the minus signs.
Question for you. On that bottom, the very bottom row you did there, let's say the second to the third term, when you pull that I out and it becomes a -1, is that what flips your plus minus in the next
Yes.
term? Okay.
Okay, so let's use that. Let's go ahead and use that relationship now. So recall that we denoted our angular momentum basis kets. We wanted to denote them as lambda and then m. And we wrote down what happens when you operate with jz and j squared on this ket. So now let's consider what happens when you operate with jz, j plus on the ket lambda m. Okay, so we don't know what j plus does to this ket, but we know what jz does because we already defined that. We defined that jz on lambda m was h bar m lambda m. That's all we know. So what do we have to do? We have to use the commutation relation that we just defined. So we just found that JZ, J plus minus J plus JZ was equal to plus J plus H bar times J plus. Okay, so the only thing we can do is substitute this in here. So just solve this thing for J plus, JZ, J plus. So JZ, J plus is H bar J plus J plus JZ. And you'll notice that when you do this, you've flipped the J plus and the JZ so that this thing will now operate on the ket and give you something that you know. So J plus JZ, J plus on ket lambda m will give us H bar J plus on the ket lambda m plus J plus JZ on the ket lambda m. And we already know that this gives us m H bar times the ket lambda m, so that JZ, J plus lambda m will just give us H bar plus m H bar J plus lambda m. Okay, so to summarize that, we have JZ, J plus lambda m is H bar m plus 1 J plus lambda m. Well, this is an eigenvalue equation. And so is this. It's an eigenvalue equation where the eigenket is this thing. So the eigenket here is J plus acting on lambda m. Okay, so JZ pulled out the m, okay? It pulled out the m in this ket. So after J plus acts on this ket lambda m, it clearly does something like increase the m value by 1. So that's exactly what's happening. So the eigenvalue is H bar m plus 1. Okay, so now you can kind of get an idea what these ladder operators are doing. So we've just algebraically discovered what we've already found with the matrix representations. So if you were to operate, when you operate J plus, you kick up the m value of the state of the ket. Okay. Okay, so let's do that here for J minus. For J minus, we would consider JZ J minus on the ket lambda m. But JZ J minus, again, we don't know how J minus acts on this ket, just JZ. So we have to do the commutator again. So we have the JZ J minus minus J minus JZ is equal to minus J minus. So that means JZ J minus is equal to minus J minus plus J minus JZ. And then we can substitute it. So we'll have minus J minus on lambda m plus J minus JZ on lambda m.
Don't you need an H bar somewhere?
Yeah. Okay, and so we'll have minus h bar, j minus lambda m, and then again, this will pop out an m, so we'll have plus m, h bar, and then j minus on lambda m. So this will give you then m minus 1 times h bar lambda m, oops, j minus lambda m. And this is jz and then j minus lambda m. Okay, so it's the same kind of equation, just lowers it by 1. Okay. Now, something important to note is that if we calculate j squared, the commutator with j plus minus, this is just 0 because this is just jx plus or minus ijy, and j squared commutes with all of these things. J squared commutes with jx and jy. Okay? So it doesn't matter how often, it doesn't matter what, so j squared on lambda m is not the eigenvalue of j squared is not going to be affected by j plus minus. Okay, because it commutes, so you can always just swap them. And that's important because that means that, you know, we're characterizing our kets by m, but this lambda remains the same no matter what we do. And so now we want to calculate what that lambda is so that we can finally fully characterize our states.
Can you leave that last line down there just for a second?
Down here?
Yeah, just for a second.
Oh, sure.
Thanks. Okay, I got it. Thank you.
Okay. Okay, so again, we defined that the total j squared was jx squared plus jy squared plus jz squared. And j squared minus jz squared is equal to jx squared plus jy squared. This thing is, it's, both of the operations here are squared. And these are Hermitian operators, so we know they return real values, real eigenvalues. So this thing is positive. Now this is going to be something like, remember how we defined j squared on lambda m? That was equal to h bar squared lambda m. So this is something like lambda minus m squared. Okay, and so we expect lambda minus m squared to be greater than 0, or lambda to be greater than or equal to m squared. Okay, that's just you know, sort of a hand-waving argument here, but what we expect. Now we said if we were on the top rung of the ladder, you can fall off. So there must be some maximum value. so j plus of lambda m max was zero, okay? So if there was some maximum value of m, we fall off the ladder and we get zero. So let's call m max little j, so j plus lambda j equals zero. All right, so, and then just trivially, we'll write j minus j plus on lambda j is equal to zero. I didn't do anything, I mean, I'm just multiplying it on the left by j minus. But now we can actually multiply these out. So we'll have jx minus I jy, jx plus I jy. Let's just calculate what this operator is first. That's jx squared, and then I'll have plus I jx jy minus I jy jx, and then plus jy squared. Okay, so this is x squared, this is jx squared plus jy squared. That's just j squared minus jz squared. And then this here, this is plus I, and then we'll have jx jy minus jy jx. So this is j squared minus jz squared plus I jx jy minus jy jx. This is I h bar jz. So that's minus. So this will be j squared minus jz squared minus h bar jz. That's that operator, j plus j minus. So let's let it operate now on this lambda, and on our ket lambda j, and see what we get. So we'll have j squared minus jz squared minus h bar jz operating on lambda j, and that has to equal zero. But we can just go back to our definitions, what we wrote down for jz and j squared. So this will give us lambda minus h bar squared j squared, and then minus h bar j, h bar squared j. And this has to equal zero, and that gives us lambda. So lambda is equal to h bar squared, and then we have j squared j plus 1. That's the way to write it, and that's it. So now we have the top rung. Okay. And then we have to figure out the bottom rung. So we'll have, suppose that J prime is the lowest value of the Z projection of spin. So we'll have lambda J prime, we'll have J minus now, and we'll let J minus act on the state of lowest spin, and will give us a 0. And we can just do then trivially J plus J minus, and we'll do the same exact thing we did over there. So now we'll have Jx plus I Jy and Jx minus I Jy. And this is equal to Jx squared again plus Jy squared. But now we're going to have the y and x is reversed here. So this will be, instead of, well, let's just work it out here. This is I, jy, jx minus jx, jy. So this is j squared minus jz squared. And then jy, jx, this is in the wrong order, so that means we get a minus sign, so we'll have we'll have plus I times minus I jz. So this gives us j squared minus jz squared plus h bar jz. And so when we let it operate on this ket, we'll get lambda this thing is lambda minus h bar squared j prime squared plus h bar squared j prime. And that has to be equal to 0. And so this occurs when j prime is equal to minus j, where j is the maximum, okay? So the minimum rung here is minus j. So let's go ahead and see what that, now we can redefine our basis kets. And we'll have a nice picture here. So let's relabel the kets with j and n, where j is the maximum positive value. So that's the maximum positive spin projection. Okay, and then m again is the z, just the z projection. Of the spin. So now we have j squared acting on jm gives us h bar squared j plus 1 jm. Okay, and our states go from plus j, j minus 1, j minus 2, down through 0, minus 1, down to minus j. So the total number of states for particle with spin j is 2j plus 1. Okay, there are 2j plus 1 m values. Okay, so for spin 1/2, j equals 1/2, and we have 2 times 1/2 plus 1 is equal to 2 states. Right, that's for our electron. And for spin 1, j equals 1, and then we'll have 2 plus 1 equals 3 states. And then, for example, spin 2, j equals 2, and this would be 4 plus 1. It would be like 5 states, this would be for the graviton. Graviton's a spin 2 particle, it has five states, but you only can see 2 of them.
But gravitons actually exist?
Hmm?
Does that gravitons actually exist?
Yeah. Yeah, absolutely. That's what the gravitational wave detector confirms.
They confirm that the particle exists. I know that they've confirmed that like gravitational waves.
Any classical field can be interpreted in terms of particles.
Okay.
Okay, so let's do a more, let's consider a spin 3 halves. So a spin 3 halves particle, anything with half integer spin has to be a fermion. But, you know, let's forget about fundamental particles that have spin 3 half for a moment and just think about some real things that do have spin 3 halves, like nuclei that you can do magnetic resonance imaging on. They have 3 halves, they have spin 3 halves, and you can see all of these states. So for spin 3 halves, then you would have a top state. So we would denote it 3 halves, 3 halves, and then we would start going down in units of 1. So 3 halves, 1 half. 3 halves minus 1 half, and then 3 halves minus 3 halves. Okay.
So 4 states?
Yeah, so yeah, that's right, right? So 2 times 3 halves plus 1 is 4.
Okay.
Okay, so then we would, for our electron, then we would label the states one half, and 1 half minus 1 half. And this would be, you know, it could be any of our states, but it would be, you know, Z plus and Z minus, or it could be X plus and X minus. It depends on what instrument you're putting it through, but, so you could label the base states, you know, using this notation, in terms of J and M.
The Z plus, you put Z minus in it.
Oh, yeah, this one would be a Z plus. Okay, so the other thing to notice is that the M max is equal to J, but J squared is equal to J plus 1. Okay, so what that means is you can't ever align the z-axis of your particle along your instrument z-axis. I don't get this full value here, right? This is bigger than J squared, this is bigger than J squared. I mean, so J total, right, is equal to the square root of J plus 1. So you can't, if you draw a picture of these things, we can draw, for example, this one, you know. We could, this. Right, if this is, J, let's see, this is 3 halves, this is 1/2 minus 1/2 and minus 3 halves, right? But J plus 1 in this case is, it's a 3 halves spin. 3 halves plus 1 is 5 halves, so this is equal to 15 halves. Okay, and if we take the square root of that, so let's, square root of 15 halves is, you know, it's somewhere up here. So I can't, I'm getting the z projection of this spin
Okay.
here, but it's not, you know, I mean, if I could really align the particle right with my z-axis there, I would get the full j squared, but I can't do it. Okay, so that's another illustration of sort of the strange facts about quantum mechanical angular momentum. Okay. So we know how to label our kets, and we know the maximum value of the spin and all of this. Now let's go ahead and see what happens. We want to calculate some of these coefficients for when we operate on a ket with J plus or J minus. Okay, so let's calculate the matrix elements of J plus and J minus. Okay, so we did this already when we just defined what J plus and J minus were. We already had Jx and Jy. Although I didn't show you how to calculate those yet, but in any case, we want to do this now in a more general fashion, using what we now know with our, our state kits here. So if we operate on some state kit with J plus, that just gives us some other ket. We know it has an m plus 1 in it. Right? We know that this is something like, it's some constant times h bar, because this thing has units of j, and then this will be j m plus 1. Okay, and now we can just take the inner product. On this kit. And that will be then the broad Jm times J plus dagger J plus on Jm. I just turn around this ket, and that gives me a J plus here. But J plus, we already know what that is. That's J plus dagger. This is just J minus. So I already erased J minus J plus, but that's what we need. J minus J plus, again, was, let's see, J squared minus H bar squared, no. Is it H bar JZ squared, JZ squared minus H bar JZ? It's minus JZ squared minus H bar JZ. Wasn't that it? Okay, so we have, let's see what this is. So if we plug it in, we'll have Jm, and then we'll have J squared minus JZ squared minus H bar JZ, Jm, but this is equal to what? This will be equal to H bar squared J plus one, minus JZ squared will be H bar squared M squared. And then this will be minus H bar squared M. Right, and then this will be Jm. Okay, but we already assumed that this, that these are orthonormal states, so that's one. Okay, so now let's plug in this thing up here, because we know that whatever J plus does, it increases this state by one. So now we'll just have, this has to be equal to, so if we have J M plus one, C plus complex conjugate, H bar, C plus J M plus one, this is equal to this. So here we'll have the magnitude of C plus squared times H bar squared, and that's equal to this, times J M plus one, J M plus one, and this is just one. So we have magnitude of C plus squared times H bar squared is equal to this. So what is this? This is H bar squared, JJ plus one minus M plus one. Okay, so we can cancel my H bar squareds, and I just have that C plus is equal to the square root of J plus one minus M plus one. Okay, and so that's a mess, but that's how you get it. So when J plus operates, it gives you this whole mess back, depending on the J and the M values. And then C, if you operate with C minus, so if J minus on Jm gives you C minus H bar Jm minus one, then C minus is equal to the square root of J plus one minus M, but now it'll be an M minus one. Okay, so let's check this. Our formulas here, and so for J equals one, we have J plus on 1 equals 0. J plus on 1 0 is equal to H bar. Wait, it was more than, it was radical 2 H bar. Times the top state, right? And then J plus on the bottom bottom state was also root two H bar, now times one on the middle state. Right? That's just in our new notation. And now let's go ahead and see if this is correct. So we will, again, we'll assume that J prime, M prime is delta J prime, delta M prime. We should have orthonormality on our basis states. And so we can just calculate the coefficients then. Oh, well, I mean, I'm not gonna use, I suppose we could go and use the formulas, but you can just check. I mean, so let's pick this one because M is 0. So if I operate with J plus, when my spin is 1, but J is 0, M is 0, so that means these terms go away. And J is 1, so I'll have a 1 here, a 1 plus 1 is 2, so C plus will be a square root 2. Okay, so you can check that those all work. And now if you just take the inner product with, all of these base states just turned around. Then you'll find J plus is equal to, let's see, it's only gonna, this is only going to give a contribution when 1, 1, so 1, 1, 1, 0, 1, 1, 1, 0, so this will be a root 2 H bar. Okay. Any questions?
A lot, but I'll save it for later.
All right, well, I went pretty fast through that, so I'm gonna, we have 15 minutes left, but I think that's a good place to stop, so you can ask questions about what we covered today.
So just a curiosity, when we're dealing with spin 1/2 particles, we're dealing with 2x2 matrices, we're looking at spin 1 particles, that jumps up to 3x3. Like when you're dealing with like gravitons with 5, do the matrices just get progressively
Bigger, yeah.
larger and more ridiculous?
Yeah,
Like-
I mean, in practice, there's, unless you're doing magnetic resonance where you actually you can have spins that are like 9/2 and stuff like that. You can have big, But for elementary particles, it's pretty simple, actually.
Usually, you probably have computers or something to do the big matrices at that point.
Yeah, I mean, I think everybody, anybody who does calculations these days, you use some kind of a numerical approach.
I don't know, thinking about spreadsheets and slide rules sounds like it might be fun.
Yeah.
So I have a question about these, so JX, JY, and JZ,
Yes.
are these like actual orientations in space, or are these like a state space that doesn't really?
They're operators.
They're operators.
They're operators that
Right.
are, they're the generators of rotation, and they're operators on our Hilbert space. So they, so we could draw a picture. So for spin one, the Hilbert space, it's the span of the vectors, 1, 1, 1, 0, and 1, minus 1. So that means any ket that has coefficients such that mag C1 squared plus mag C2 squared plus mag C3 squared equals 1. That defines the Hilbert space. So that's that's the space of all the vectors.
Right.
And Jx, Jy, and Jz, if I put the hats back on them, are operators on the space. And they satisfy those commutation relations.
Okay. So then the X, Y, and Z, they're just labels, they're not actually corresponding to free space.
Well, I mean, we're in three-dimensional space. The SG measurements are in three-dimensional space. So we are talking about angular momentum in those directions. Right. But these things aren't really vectors or anything.
I see, okay.
Right, these are the vectors.
Right.
And these things are the operators that operate on the vectors.
Right. I guess I was just confused, like, why they were called X, Y, and Z, as in, like, how do you pick which one is which?
Well, I mean, because you're in three-dimensional space and you make those measurements on the SG instruments. Right. And so you're talking about the spin aligned
along one of those axes.
Along one of those axes, yeah.
Okay.
But it's not actually ever really aligned on the axis, right?
Right, it's just you're measuring along that axis.
You're measuring along the axis and you get some Z projection. So,
I think what just confused me was that the matrix representation of those operators. I don't know, I guess this is more of a conceptual question that won't be on the test, but so all the operators are so like the matrices are different, but I was just kind of confused at if the space is symmetric in all three directions, then why do they look so different? Does that question make sense? Like if you're measuring along the Z-axis.
it's because we're in one basis, right? If in the Z basis, JZ in the Z basis is 1, 0, minus 1.
Right.
But JX in the X basis is 1, 0, minus 1 in the X basis. So it's once we pick a particular basis and say what's JX in the Z basis, then we get the 0, 1, 0,
Okay.
1, 0, 1. Right?
Okay. It's just
that's an artificial thing because we're picking, we're making the choice.
right.
But there's no, this commutation relation here, this is a statement that's completely coordinate free. It does not depend on any directions in space.
Right.
So this is a really this is the most general statement about angular momentum.
Right.
This is just, well, we picked a basis, let's represent it, and now we're gonna get down to like a coordinate basis.
Okay. Okay, that makes sense.
You remember like when we did the Z plus is 1,
Yeah.
0, Z minus is 0, like once you choose that, the math like defines the other ones, right? Like you make your choice there and everything else follows.
Yeah, that's why if you take a class in general relativity, the one thing that you learn to do is you want to work with tensors that have no coordinate system associated with them.
Well, I would love to take a class in general relativity.
Well, tell the chair that you want me to teach the class and I'll do it.
Yeah. Wish that was the elective I could have taken.
Right?
As I wish that was the elective I could have taken. I nailed general relativity in modern physics.
Do you graduate this semester or next semester?
Next semester.
It's not too late.
That's true.
I'm pretty good at twisting Dr. Gibbs' arm, maybe I could have a talk with her.
She doesn't really require that much twisting. It's usually like, we'll do whatever we want as long as it's like possible.
That's true.
You, like, the kind of the permission, the kind of permission she gives me to just do whatever is kind of crazy.
What we could do, I mean, I don't wanna teach 3 courses. Two's plenty, but, what we could do is, have a directed readings
Okay.
course where we have multiple people.
Mm.
And then, you know, we could go through it that way, so,
That's true.
if you wanted to still have exposure to GR.
I just remember like doing general relativity, like that was when I was doing the math and I was actually having fun with it. Cause like, I don't know how it is, how it works in my brain, but there are just certain math concepts that really click and I like doing the math on. And that's just one of them. Then orbits, though, I haven't gotten to much with orbits yet.
Yeah, I mean, the issue is if you really wanna learn GR, you really need to take differential equations.
Yeah.
Okay, it's not, I mean, it's cool.
Um,
I did that.
I mean, you can't go very far without knowing some differential geometry. Sorry, did I say differential equation?
Yeah.
Yeah.
I meant differential geometry.
Oh, yeah. You see, I want one of those too.
Yeah, that's a,
S&T was going to have one, but then 3 people signed up, so they just didn't.
well, nudge the chair and, see what she says.
Okay.
Oh, thanks.
All right, any other questions or?
I mean, I got stuff I wanted to ask you about that I've been working on, but it's all kind of like old hat for what we're doing now, so I didn't want to like waste anybody else's time with it. So if anybody's got stuff about like this, then feel free.
No questions as of yet.
Go study tomorrow.